Hey everyone, welcome to the last paper session of this amazing I3D, another amazing I3D. My name is Jamie Excel and I'll be chairing this session. I'll be doing the least important work here. So we're gonna have three papers. The first one is Windblown Sand Around Obstacles, Simulation and Data Validation of Deposition Patterns.
Recording in progress.
Our speaker is going to be Nicolas Rosen, and Nicolas is graduated from Telecom Paris. Now he's a last year PhD student at INRIA and the Graph Deco team. Is interested in physics-based simulation and the accuracy of simulations for using computer graphics. And so we're ready to listen to it, right?
Thank you for the introduction. Yep, thank you. Yes, so about that, we'll see how our graphics tool are accurate to simulation sand deposition today. So again, this is a joint work with my supervisors, Régis Duvigneau, Adrien Bousseau, and Guillaume Cordonnier. My talk is about windblown sand around obstacles, simulation, validation of deposition patterns. So sand covers around 7% of the Earth's surface and is present in various environments. And these varying conditions under which the sand is blown by the wind produce richly diverse sand dunes and patterns. So to see a bit what they look like, we can have a look at Google Earth. So here I zoom in a region between Morocco and Western Sahara. And we can see that as I zoom in, we can see these intriguing patterns appearing. So these, for example, are Barkhan dunes. We'll come back to them a bit later. And we see that here there's a whole field of them. So it's quite intriguing. These fascinating, on the one hand, these fascinating sand dunes are iconic landmarks of desert sceneries. And on the other hand, sand can interact with human infrastructure and cause damage on it. So therefore, being able to quickly and accurately simulating them is both useful for creating desert sceneries in movies or games, but also for mitigating the impact of sand on human infrastructures. So let's see a bit how previous work simulated sand. So we'll start with methods that are fast and plausible. So the first one I'm going to talk about is one of Paris and colleagues, which is called Desertscape Simulation. So here they have a fast and controllable method that enables the user to remove sand in some areas and add it back in some others, while creating a realistic, like a satisfying desertscape. But they are not able to handle obstacles. This is why in this same conference here at I3D last year, Taylor and Kaiser proposed a follow-up of this paper that is still fast and controllable, and they tried to add obstacles in it. So here their method is able to have some obstacles in it, but we'll see that the way they handle them is quite limited and not that accurate. Other works have came up with handwritten rules to describe how the sand is supposed to erode and deposit around obstacles. So here, for example, they take the example of a cube, and they say, okay, the sand is supposed to be eroded in some area, and is supposed to deposit in some other. But the problem here is that you have to come up, if you change the obstacles a bit, you have to come up with a new set of rules. So it's not robust at all to handling various obstacles. So that's why we want to avoid such methods. So now if we want to avoid these methods, one thing we can think about is to model and to simulate the wind above the sand bed and see how it erodes and how it erodes the sand. So this is what the computational fluid dynamics has been interested in. Here, for example, I'm going to talk a bit about this paper in this presentation of Lo Giudice and colleagues. Here they couple an accurate twin simulator with a sand transport algorithm to produce really precise sand dunes and deposition patterns. The main drawback of their method is that it's really expensive. It can take up to days to run, but it is really precise and it can handle obstacles pretty accurately. So what we want to do is to take inspiration of these methods, while doing something that is way faster. So to summarize a bit the previous work, we have the graphics papers that are really fast. Actually, they're interactive, but they struggle to handle obstacles and they are not that physically accurate. We have the CFD methods that are really slow, but that can handle obstacles and that are accurate. And we propose a trade-off between these, and we'll see how we perform. So let's describe a bit how we do that. So first, I'll introduce a bit the concepts we need to describe sand transport. So for this, we'll start with an initial sand bed here in 2D for the sake of clarity. So if we want to know how the sand is transported, we first have to consider that a wind will flow above this sand bed. So here is just a schematic drawing of it. And because the wind flows above it, sand will be eroded in some areas, it will be deposited back in some others, and there will be another phenomenon which is avalanching, which will make sure that there is no slope greater than a certain threshold in the scene. So these are the main concepts that we will try to implement. So let's see now how we do this. So as I said, let's start with an initial sand bed, and let's call this sand bed H. So what we want to do is to know how it evolves over time. So this is why I write the derivative here. So the first thing we'll do is to simulate we'll quickly simulate a wind above it, and we'll call this wind field U. And depending on the values of this field U, we will compute some fluxes which will describe how the sand will be transported from some cells to the others. And once we will have computed these fluxes, we'll take the divergence of them and we'll have the updated sand bed. So now I'll describe how I compute every one of the terms. So the first term is the wind. So for the wind, we propose to use the well-known stable fluids methods that is known to be useful to simulate, for example, smoke. The paper was published by Jostam, and we'll see that it is accurate enough to model sand transport. So now for the Q term. For the Q term, I'll explain a bit how sand is transported by the wind. So there are three main modes of transport for the sand. The first one is the bed load transport. This is when particles are creeping alongside the sand bed without leaving it. The second mode is saltation. This is when particles are leaping from some areas to others. And the last one is suspension. So suspension is the one we are maybe more familiar with because it's when the sand is actually blown by the wind. And for example, this is the phenomenon that explains why we have sand coming from North Africa to Europe, if you know a bit the Sirocco wind. And according to the literature, the saltation mode explains around 80% of the sand mass transported. So in this paper, we'll only focus on this mode of transport, which is saltation. So very quickly, how do we compute this QS? We have the sand bed H. We compute with stable fluids the wind field U, and we'll just take the values of U that are really close to the sand bed. And by doing this, we will transform our field that is 3D in a 2D field, very close to the surface. And this will give us the wind values U star really close to the sand bed. And from these values, we'll borrow an equation from geoscience that says that the saltation flux is equal to basically some factor times this field to the power of 3. So this is how we compute the saltation. And then, as I said, there is a second phenomenon, which is avalanche, that makes sure that there is no slope greater than a certain threshold. And for sand, this threshold is more or less equal to 30 degrees. So here, this is the only equation that I won't describe that accurately, but we'll just see that we have our threshold theta here that comes into place. And just to see what it does when I run some steps of it, it just converts our cube to something that looks like it, like this, like a cone. I made this experiment just to make sure that it also works when I have a step, for example. Okay, now that we have our two terms QS and QA, the last step is just to make sure that is just to clamp these values. It is just to make sure that if the wind is really strong in an area and that sand is supposed to be eroded a lot, this clamping function is just here to make sure that there is actually sand to be eroded here. Okay, so now we are ready to update our sand bed H. So we'll do this in an iterative manner. So we have our sand bed H, we'll simulate the wind U, we'll compute the updated H at time t+1, and we'll just iterate over this to simulate this coupled phenomena. Okay, so combining these, now we have everything for our simulator, and combining these ingredients is fast. So here I just provide some timings. It takes tens of seconds to some minutes, depending on the resolution. I provide more timings in the paper. It is able to handle obstacles, but now we'll see how accurate this is, and this is what the remaining of the talk will be about. So to evaluate this, we'll first see if the wind that stable fluids produces exhibits satisfying patterns or not. Then we'll see if the erosion and deposition patterns around obstacles are accurate or not. And then we'll see if our method still enables typical sand dunes to emerge or not. So first, the wind. So here, this is the paper that I talked about in the related work by Lojudic and colleagues. Here they took a sand bed in 3D. They run a really precise 3D solver to see what the winds looks like. And here they just redrew what they obtained. So this is a schematical representation, and we just compare very quickly to it to see if we have more or less the same patterns. So this is what we obtain with the stable fluid solver. So we do have the recirculation area in the wake of the field. And if we just run one step of our iterative algorithm, so just one step, we see that the sand is indeed eroded above the dune, and that it is deposited back in the wake of it. So with this experiment, we just can say, okay, it should work, it could work, but let's see how it actually performs. So now let's see if it does well around obstacles. So for this, we found a nice measurements that were done by Popema and colleagues. So this is a team in the Netherlands, and here they went on a beach in the Netherlands. They placed some obstacles on sand. They waited for the wind to flow during the night, and after that they just measured what was the height above these obstacles, and they tested different arrangements of these cuboids. So this provide them this kind of measurements. So this is a photograph on the left and a height map on the right. So here, very quickly, the red is where the sand is deposited, and the blue is where it's eroded. And I have a whole bunch of them that we can compare against, depending on the different arrangement that they measured. So here we have the wind flowing in this direction. This is their measurements on the right, and our simulation on the left. So we see that we are able to model the deposition pattern before the cuboids, also the erosion patterns around the cuboids, and more interestingly, we are able to model the deposition pattern in between the obstacles in the wake of the flow, and also outside it. So then we can watch a bit the other measurements. I will spend less time on them. And here with this one, where the obstacles are closer, we see that we reach a bit the limit, where some deposition patterns, like the one before, are quite accurately reproduced, but the one in between are less accurately reproduced. And interestingly also, we see that for the cuboids that are further away, the deposition patterns before them are separated in the two on the right, but on the left, they are grouped. And we see that our simulation is able to model this phenomenon, so it is quite interesting. So in the paper, we provide more arrangements. For example, when you have the wind flowing with a certain angle on the cuboids. And I'll just spend a bit of time to compare to the previous work. So here, this is what the Taylor and Kaiser paper proposes as a deposition pattern around the cuboid. And this is what Popema actually and colleagues actually measured on the field. And this is what we obtain shaded in both ways so that we can compare accurately. And we see that we are more able to have this horseshoe pattern around the cuboid, the erosion pattern. Okay, so now we see that we have satisfying results for the obstacles, and we want to know if we are still able to let the sand dunes that we like emerge. So for this, we just consider typical sand dunes shapes that are Barkhan dunes that we saw previously and star dunes. So beginning with Barkhan dunes, according to the literature, Barkhan dunes are supposed to be shaped on terrains that have very few sand supply and that have just some stacks of sand. So this is what we reproduced here. And they are shaped when the wind flows in one direction, one main direction. So this is what we asked our algorithm to do. And this is just a quick visualization with Houdini. And here we see that the Barkhan is starting to be shaped. And here we didn't mention anything else than what I said. It just emerges by itself. And here we just compare to an image of a Barkhan dune taken by someone doing a hike. And just to have an idea of the size of the thing, these are people standing on it. So now we also compare to the star dunes. The experimental setup is really similar. We also have a small stack of sand, but this time we have wind flowing from several directions. So it could be 3, 4, 5, 6. Here I do 5. And this is again the Houdini, a quick Houdini visualization of what it does. And we see that we have this nice star dune that emerges. Again, we didn't say anything else that what I mentioned to the simulator. And here we compare to a group in Paris that is expert in sand dunes. And we see that both for the 3 arms one and for the 5 arms one, we have very similar patterns that emerge without specifying anything. And here, very quickly, we compare to images of sand dunes of star dunes in the wild, just to see that it's quite similar. Okay, so as a conclusion, we propose a fast simulation of sand erosion and deposition that is based on stable fluids and that combines siltation and avalanching. We are able to capture typical dune shape and to accurately reproduce erosion patterns around obstacles. So we use a height field to describe the sand. This comes with compromises. For example, we have a staircase-like patterns, artifacts that you might have seen in the simulations. And also we are not able to represent overhangs for the obstacles and also for the height field. And this could be useful to investigate this because, for example, some papers have come up with strategies to trap the sand to prevent it from accumulating on railways, for example. And you can see here that they do have overhangs. Then everything that I said could be applied the exact same for snow sceneries. The only thing is that you would have to model also the state changes to be able to accurately model them. And the last thing for designing purposes, there have been recently a trend of papers that investigated how we could mitigate the sand impact on structures. So very briefly, here on the right, you have the structure that you want to protect from the sand, because if the sand accumulates on it, the house will basically collapse. You have the wind coming from the left here and some sand bed. And what these papers want to investigate is, can we put some obstacles in the middle that are called sand mitigation measures to try to deviate the wind and to prevent sand from accumulating on these structures? And we think that our method could be really useful in this use case, because we have patterns that we obtain in a fast way and that are quite accurate. So this could be really helpful for this, and this could motivate future work as well. And yeah, again, thank you for listening. And we have the code available here and the project page here if you want to have a look. Thank you.
Very nice work.
Thank you.
That's yeah, very nice work. And we have time for questions. Anyone with questions? If not, I can start with. Oh, you have one. All right.
Hey, great paper. Also, like this entire field, and we're lucky that I3D just is a host to sand papers for some reason.
Yeah, I agree.
Oh god, this joke landed flat this year as well. Modeling state changes. You mentioned that there's this is the challenge of switching domains. Can you expand on that and like even without snow, talk about like wet sand, for example, or different types of sand.
Yeah, that's
different types of dust.
Yeah. So very quickly, So, for example, with this slide here, for example, so what I do is that I simulate the wind with stable fluids, and then I convert it so that I have only the values just above the sand bed. But if you have overhangs, for example, in your snow patterns, you would have to think about using something else than a height field, because you would also have to erode it from beneath. So you don't only have a 3D to 2D conversion, you have to do something more 2.5D, I would say. And for wet sand, there are some, very quickly, where is it? Yeah, let's say here. So wet sand, the main thing that changes is that it just has different properties than the sand that I'm considering here. For example, the rest angle here would be a bit different, and also maybe this one here, this equation would be the same, but it might have different coefficients, for example. And this is the same, for example, in people are like trying to study how sand dunes are shaped underwater, or for example in other planets like Mars, like people like to do it, for example. So the concepts are the exact same, and the algorithm could be reused. You would just have to tweak a bit the parameters so that it actually corresponds to what you want to model.
Right. Any other questions? I would like to ask one, actually. You talked about the realism of the simulations, and there's some limits to it that you emphasized. I would like to ask you, like, where is this coming from? Like, what do you think is the limiting factor in terms of achieving the realism that you would like to?
So I think that one. So I think there are two things. The first thing is that we want to be fast. So as I said, it can take tens of seconds or minutes to run. And by doing that, I think that we just so in the air simulation, there's an incompressibility that you have to satisfy, and this is the bottleneck of this whole simulation, because this is the only thing that takes time. The whole sand simulation is 2D, so it's like instant to run. So we just have to have a compromise between being accurate or not for this. If you want to do it fast, you'll do the incompressibility less accurately. And the other thing is that by using stable fluids like simulations, there is something called what's the term in English? Artificial viscosity. That comes with the fact that your meshing, or like for us here, it's a grid. It's really coarse, and so if you do the math, there is a term in the viscosity that will be added, and that basically makes you model a phenomenon that is slightly different from the one you would like to model. And so, yeah, instead of I'm saying random numbers, but if you want to model something with a viscosity 1, it's not that, but you wouldn't be able, because no matter what you do, you would have like 10. So you can't be under that. So there are some phenomena that you would struggle a bit to model with this algorithm, but it's still quite accurate as we saw. Yeah.
So I'm hearing that the big problem of like accuracy is the fluid solver itself.
Yeah, but yeah, exactly. But what we wanted to show here is that even if it has drawbacks in terms of accuracy, and it is not necessarily meant for that, in the case of sand simulation, it works great.
It definitely does. Yes. That was great work. Let's thank our speaker again.
Thank you.
So our next speaker can come over here. Okay, we're ready. So our next talk is going to be by Chunlei Li, the first author of this paper, a unified particle-based solver for non-Newtonian behavior simulations. Yeah.
Hello, everyone. It's an honor to be here to present my recent work published in TVCG named Unified Particle-Based Solver for Non-Newtonian Behavior Simulation. Please forgive me for reading the notes because my English sucks. So let me begin my presentation. We will give an intuitive introduction to our particle-based non-Newtonian solver, and then present additional visual effects of our experiment. Our solver is focused on the non-Newtonian behavior simulation, which is a classic topic in graphical community. Compared to other works, our work stands out in the following three aspects. First, our method is purely particle-based. By simply modifying the stress term and the of the NS equation under SPH framework, our solver covers a wide range of rheological materials, including substance from fluid-like to solid-like. And second, we have implemented 6 classic shear-dependent viscosity models. These models are able to simulate shear thinning, shear thickening, and that's from the slides. Okay, can I turn it off? Yes. Okay. So. Thank you. Second, we have implemented 6 classic shear-dependent viscosity models. These models are able to simulate shear thinning, shear thickening, and Bingham fluid behaviors, which collectively encompass the majority of non-Newtonian phenomena. Third, we elegantly and concisely integrate viscosity, elasticity, and plasticity in one unified framework. We utilize the generalized Maxwell model to vividly and physically meaningfully to interpret our constitutive model. Non-Newtonian fluids differ from the Newtonian fluids in that they display nonlinear stress-strain rate relationships. There are 2 types of nonlinearity, the time-independent and time-dependent. For the time-independent nonlinearity, we can use the shear rate-driven models to give a spatially variable viscosity to model it. As shown in the diagram, shear thickening fluids exhibit an increase in viscosity with the increasing shear rate, and vice versa for the shear thinning fluids. Bingham fluid type, including the Carson fluid, has a non-zero stress at the 0 shear rate. For the time-dependent nonlinearity, we modeled viscosity, viscoelasticity and plasticity with generalized Maxwell model, which will be discussed later. The major difference between our algorithm and others lies in the inclusion of both viscous stress and elastoplastic stress in the Navier-Stokes equation in our solver. This is the key feature of that enables our solver to handle non-Newtonian behaviors. We introduce the generalize the maximum model to provide a physical, meaningfully explanation of the viscosity, elasticity, plasticity, and their interrelationship. In this diagram, the spring represents elasticity, the slider represents plasticity, and the dashboard in the bottom represents viscosity. Total stress is divided into elastoplastic stress and viscous stress. The elastoplastic stress is controlled by the elastoplastic strain, which is further divided into the elastic strain and the plastic strain. While the viscous stress is controlled by the viscous strain rate and the viscosity. From now on, we will demonstrate several experiments and comparisons. Our SPH-based solver effectively tackles the high viscosity and supports additional features such as elastoplasticity and non-Newtonian viscosity. We draw a comparison with two state-of-the-art frameworks, the FLIP by Shao et al. In 2022 and the MPM by Fang et al. In 2019. Our framework demonstrates comparable results to other two frameworks in simulating the falling of a viscous cowl. Our framework not only handles high viscosity fluid effectively, but also supports shear-dependent viscosity, viscoelasticity, and viscoplasticity. This extends its compatibility beyond the traditional approach for modeling complex fluid behavior. In this scene, the upper row tomatoes show solid-like behaviors with different elastoplasticity, and the lower row tomatoes shows fluid-like behaviors with different viscous models. So in this scenario, 8 viscous armadillos sliding down a slope. Each armadillo adopts a different shear-dependent non-Newtonian model, including the Cousin model, power law model, Cairo model, Cross model, and the Bingham model, and Herschel-Berkeley model, among others. We have successfully replicated a classic non-Newtonian phenomena, the impact of a golf ball dropping into a mixture of cornstarch. Due to its shear thickening properties, the ball experiences a rapid impact followed by a slow sinking motion. Our simulation closely matches the recorded video results, demonstrating a high level of consistency between our model and real-world observation. The color of the particle in the particle wheel represents their strain rate, and the line plot on the right shows the change of strain rate and max viscosity during the process. If we keep the other setup and only change the fluid from cornstarch mixture to ketchup, which is a shear thinning fluid, we will see completely different behavior. With the implementation of diffusion equation, our solver is able to simulate phase change, such as the ice cream melting. Thanks to the particle representation, our solver is easy to handle the topological change. For example, the chocolate bunny is cut while melting. This concludes my presentation. If you want to read the paper, you can search the paper's name on arXiv. If you want to try the code, you can search the paper's name on the GitHub. That's all. Thank you.
Yeah, that was a good talk and pretty efficient too, so we have plenty of time for questions.
Sorry, it's great. It's a great work. Do you have any data about performance? Time and
we compare the performance with the Flip and the MPM, and they just roughly the same. So
but I mean, absolutely. How much? I mean,
how much?
How much is taking and in which kind of hardware?
Like the an hour or two. An hour or two of the of one simulation.
Okay, understood. Thank you.
Now that's the entire simulation, right?
Yeah.
Okay. Any other questions?
I have a quick question. So first of all, great talk, thank you. So I know you showed how your method reacts to like a fluid interacting with a solid. So I'm wondering if you've done any work on like different viscous fluids interacting with each other.
Interacting with each other.
Different fluids sort of like mixing together. Like, what if ketchup and oil was mixing together? Have you done any work on that?
This is not my topic. This is a multi-phase problem. It's another topic, which is also a area of the simulation. So this is not our consideration, but it is interesting.
Got it. Thank you.
Any more? I am curious about one thing.
Okay.
Your solver is based on SPH.
Yeah.
Right. And you were comparing against Flip and MPM. Flip and MPM both are hybrid simulation techniques, so they use a grid.
Yeah.
To handle some of the more global motion, but you don't have that because you're relying on SPH directly. Yeah. So I was interesting to see how viscosity was very nicely handled with your simulation. Do you think a grid-based hybrid approach could be an improvement for future work on top of your work? What do you think, or is it not needed?
So you want to replace the SPH with MPM or
something like that? Yes.
There are works like that, but our solver is purely particle based. That's our feature. So the particle based has mirrors, has advantages. It can handle the topological change like the chocolate bunny case very easily. And if you have the grids, you have to deal with the like a lot of topological things. That is very difficult, and you get the artifacts. That's it.
Yes, where the particles can stick
together.
Stick together because of the grid.
Yeah.
Yes. Yeah. Any other questions? It seems like we're exhausted all of our questions. Well, thank you so much.
Thank you.
And next, we will have another TVCG paper that will be presented here. All right. This is going to be MPMNet, a data-driven MPM framework for dynamic fluid-solid interaction. And our speaker is Jin Li. Jin Li has a BS degree in software engineering from Northeast Normal University in China in 2019, and currently working on a PhD degree at State Key Laboratory of Virtual Reality Technology and Systems and at Beihang University in China. So.
Oh, thank you. Good afternoon. It's my honor to give an It's my honor to give an intuitive introduction to our MPMNet, a data-driven MPM framework for dynamic fluid-solid interaction, and then present additional visual results of our experiment. Fluid is common in nature. and everyday life, presents diverse and computationally complex scenes, will also be the subject of simulation with a wide range of applications. Machine learning-driven fluid simulation methods include fluid motion solving, pressure projection computation, super-resolution issues, and simulation detail enhancement. In the realm of accelerated computation of data-driven physical phenomena, the earliest acceleration of data-driven fluid simulation was proposed by Ladke in 2015 using a regression forest method. This method calculates viscosity integral features, surface tensor integral features, and pressure integral features, representing particle characteristics based on the positions and velocities of all particles in the scene. It then employs a regression forest model to generate the integral features for the next time step. This method can achieve real-time interactive simulation at the level of 2 million particles. It has the advantage of displacement invariance, but heavily relies on data. And due to the prediction accuracy issues of the regression forest model, the liquid surface cannot reach a completely flat state. Xiao et al. Employed convolutional neural networks for globally solving the pressure Poisson equation, suitable for large-scale scenes. This method utilizes downsampling and principal component analysis to reduce input dimensions. And Takahashi et al. Proposed a differentiable method for simulating fluid rigid body coupling, using deep neural networks to learn dynamics and address control issues. However, increasing the interactions experienced by the solid brings additional challenge. Thus, learning bidirectional fluid-solid coupling simulation will further increase the difficulty of learning and predicting fluid dynamics and solid motion. And Sakaz et al. Proposed a Lagrangian-based method utilizing interactive graph neural networks to rapidly propagate the effects of particle interactions between neighboring nodes in spatial dimensions. This method exhibits better dynamic characteristics between fluids and solids, but it is limited by the number of particles and can only predict a scene containing thousands or tens of thousands of particles. There are two challenges that arise. Compared to fluid modeling, dynamic fluid-solid coupling is much more complex, as handling and coupling the evolution and interactions of solid motion require additional expensive computations, and due to the coupling of material properties and the interaction forces of different materials within a complex dynamic system, data-driven dynamic fluid-solid coupling accelerated simulation has received relatively less attention. And there are two difficulties. The first is how to analyze and explore the computational characteristics of fluid-solid interaction simulation models, combining the comprehensive properties of numerical properties from fluid to deformable solid physical behaviors with the efficiency of data-driven models. And the second is how to achieve relevant numerical acceleration while maintaining physical accuracy, enabling efficient and accurate fluid-solid interaction in a data-driven manner. Our innovations are in the following three aspects: hybrid data-driven approach, pressure matrix representation method, and new indicator. I will briefly outline the key process of our work. First, we generate some fluid-solid coupling dataset. Here is an example of fluid-solid coupling dataset in 15 scenes over 585 frames using different subsets of initial conditions. Then we construct the pressure vectors of fluid and slip boundaries, the solid, the interface between fluid and solid bodies, and map the vectors into the corresponding Cartesian grids to obtain a suitable format for more compatible to the neural network. We use a collaborative end-to-end neural network to learn and encode interactions between fluid and solid bodies. The MPMNet contains two models, feature descriptor learning model and the future pressure learning model. Feature descriptor learning model encodes the pressure into latent space to reduce data redundancy. Future pressure learning model learns the evolution of the time dimension. In each substep, we use the inferred pressure obtained from our learning pipeline to be mapped back to the numerical solver. We also deploy a post-processing step refines the pressure of fluid and solid while reducing the inference noises to ensure the accuracy and robustness of MPMNet. For the traditional solvers, we need n and m iterations with n numerical calculations and m refinement iterations. And for our MPMNet, we use a data-driven model to replace the beginning time-consuming n iterations, and only a few m refinements can achieve good performance. By feeding the pressure properties at the beginning of a few substeps to our MPMNet, we can predict the pressure in many of the following substeps that are dozens of times the amount of the initial input substeps. I will demonstrate several experiments and comparisons. Our proposed MPMNet model can predict the motion and interactions of fluid and solid well, and we have a higher PSNR compared to other loss functions. The prediction result shows solids of different densities can interact differently with water. The line graph shows that our method achieves good fluid incompressibility. This is the predicted results of water block flushing 30 solids using our MPMNet. Even after long-term prediction, our divergence constraint is still very close to the ground truth. We have made our prediction at the resolution of cubic of 64 emitters impact solids. The resolution of cubic of 128 water block impacts 4 static cylinders and a boat floating in the waves. Our method can achieve convincing visual effects and ensure consistent accuracy. Thank you.
No, that was great. And we have plenty of time for questions again.
Thank you for presentation. I have a question about loss function. In particular, your model has 3 types of features. 2 are solid and liquid. They are 3-dimensional shape, but the remaining one is interface that is 2-dimensional shape. So how to define the loss function and add them?
We define the loss function by the pressure we got from the networks and the ground truth is the MPM framework get the pressure, the solid pressure and the fluid pressure.
They are integrated in bulk region. Pressure of
The grid pressure.
great pressure
Grid,
on
yes.
liquid region.
I can't catch you. Sorry.
Okay. I understand that loss is defined by pressure. Thank you.
Any other questions?
Ben, I'll ask Roberto's question that he always wants. Do you have any performance data as to how fast it runs the simulation?
We get the most fast on a sim about 64 faster than the MPM for the pressure solving.
Do you have any absolute numbers as to how?
Absolute numbers.
Yeah, 64 times faster, but what is?
In seconds or milliseconds?
Seconds. The seconds is not accurate. We only compute the pressure solving duration. The absolute time is not computed, and it is about because the MPM computation is about 1 hour for the whole duration, and the pressure computation is about the 30% of the whole duration. We compared the pressure computation time. It is about 64 times faster. It is the most faster thing.
Yeah, thanks. Just follow up on the previous question. May I ask, like for this specific simulation, how fast for this, how many hours, like for this this simulation thing?
For the whole duration, it is a long time.
Okay.
Because the MPM computation is a long time, about 1 or 2 hours.
Okay, I see.
Yes, and we only accelerate the pressure solving duration.
Yeah, thanks.
Yeah, I was going to ask something related to that actually. So you guys are accelerating the pressure solver that's running on the grid.
Yes.
And based on what you just said, like oftentimes the conversion from particle data to grid data and back is can be the bottleneck for MPM simulations. And this is you're not touching that part of the MPM, right? You're touching just the pressure solver that's running on the grid.
Yes.
The rest of the MPM framework is the same?
Yeah, the same.
Yeah. Really, really cool. Really nice results, though.
Thank you.
One more question? All right.
Also, just to follow the same question, yeah, I'm also curious about like the comparison between MPM and SPH-based methods for the time-consuming. Yeah, and yeah, how fast compared to SPH-based method, like compared to his work?
About SPH.
Yes, like particle-based compared to grid-based.
As you said, how long the SPH method and the MPM method.
Yes.
Usually SPH method is faster than MPM method.
Okay, cool. Yeah, yeah, thanks.
All right, let's thank our speaker again.
Thank you.